Hello guys, and welcome to my presentation. So who am I? I'm Austin Chen. I'm pursuing a career in electrical engineering. I'm a senior at Grandview, and I have skills in Linux administration, web development, and cloud infrastructure. The languages I know are HTML, CSS, JavaScript, Vue.js, C++, and Python. I am affiliated with CyberLink, Computer Science Club, and Chess Club. So, I chose this senior capstone project on modularity. So what is modularity? Well, let's first define it. It is making a product into components. So, by making the product into components, we can have less waste. It becomes upgradable, easily fixable, and it does not contribute to the problem of growing trash landfills. So let's look at a product that is modular. So this is a ThinkPad T420, and as you can see on the screen, it allows you to swap in parts such as RAM, storage, and if a part breaks, you can easily replace it. So in this laptop, it also has a CD drive. And by having this CD drive, it also fosters innovation. So for example, if you don't want the CD drive, you can also swap in a battery in the same compartment that the CD drive is in. So let's look at a modern laptop. As you can see on the screen, the MacBook Pro, it is not easily upgradable. Since the storage is soldered on, without any technical knowledge, you can upgrade the storage. However, the benefit of these soldered on parts are that it allows for more space in the components, so better performance and more compact space. However, when you want to upgrade it, you turn it into the Apple Store, and that ultimately goes to the waste landfill. So my project outline. As you can see on the screen, this is a tic-tac-toe board. So a laptop's main purpose is to have a long battery life. So you can swap in 6 batteries at the very bottom, and when you get home, you can swap in 5 processors and only 1 battery. So it gives you performance when needed and battery life when you need it. That is the purpose of the laptop. So this is my website. So the design of my website is based off of, I wanted big, bold principles that would just make the website explain itself. And my philosophy when I was creating this product is that I need to make it as simple as possible, and that I need to follow step by step. So I feel like complexity is there when you cannot simplify the problem. So this is the timeline I'm going to be following. In the first quarter, I'm going to do my website and be planning for the rest of my timeline. The second quarter, I'm going to do hardware design and mechanics. The third quarter, I'm going to do my printed circuit board, which is the motherboard, and the coding for the hardware. Quarter 4 is basically all revision and deciding on what I need to do next. So the hardware is just the physical components of the parts. So the front case. The features that this has is A. So the reason you see that the very top part is missing is for the heat to dissipate off of the top. You can swap in a keyboard, and this slot has holes for the screws and for the audio to come out. It is modular, so you can swap in the keyboard and the trackpad. It is curved, so you don't poke yourself with the laptop. So the snap-on joint. I've developed two types of snap-on joints. One is harder to remove, so it's mainly to connect the front case to the bottom case. This will allow it so it doesn't break off easily. And the bottom one is a snap-on joint that is easily able to be separated apart. So this is the calculations for my snap-on joint. That variable you see is just the deflection angle. So what is the deflection angle? It is when you bend a component and it curves to the joint. I plugged my values in and I got a value of 6,000, which is depending on the height and if, my bad. I forgot to explain what goes into the deflection angle. So it's basically the length, width, material properties of the PLA. Since PLA, it normally has a elasticity of 40. So that means it is more prone to break when you bend it. Okay, so now we have to find the deflection angle of the max. This will ensure it so that my part won't break when I bend it to the angle that I'm curving it to. So, as you can see, my deflection angle value is 6,000, while my deflection max is 7,000. So that means it just won't break when I bend it. Oh, so, and I have to multiply by 5 since if you reach like a certain percentage, like 96% of the bending, it might crack a little bit. And if you keep reaching that, it will eventually just completely crack off at 90% of the performance. So this is my monitor case. As you can see, it features a open camera system where you can cover it, so for privacy. The bottom part contains the friction joint that I will be explaining later. And to be able to use this, you just simply have to slide the LCD screen in and just screw it in. So this is the friction hinge. It's mainly based off of 3 parts. So at a certain angle, when you bend it to a certain angle, you want the laptop monitor screen to not just completely fall down. So that is what this friction is for. So I wanted to find the torque of the hinge so that the monitor screen won't just completely fall down. So that is what it is for. So the calculations for my friction hinge are that at the lowest possible opening angle and at the maximum possible opening angle of the laptop. This is to ensure that the friction hinge is greater than the torque of the laptop, so it just doesn't, fall down. Okay, so the keyboard and keycaps. I use the standard units for keycaps, which is 1 U, which is equivalent to 0.75 inches. The other keys, I will just scale them up by 2.5 inches, and the space is 1.75 inches, because that is the standard unit. So the PCB case. I originally designed it so you can swap in the PCB case easily, and at the rails you see at the top, it will easily enter the case through a rail system. However, I do not have enough CAD knowledge to be able to accomplish this. So the bottom case. Bottom case contains a heat dissipation system and a port. So I've designed this heat dissipation system off of a logarithm simply because it looks good, and that in the future I can control the angle to let more heat out or just keep the heat when the temperature is cool inside. So the hardware roadblocks. I did not study CAD for that long, and so that limited my designs to become simple. So me and my advisors. My expert advisor is Simon Young, an electrical engineer at Andes Technology. Louis Hardman, he is an expert in data science and PCB design. Grant Yoder is going to Purdue as a computer science major, so he was majorly helpful in teaching me PCB design. So this is my proof of concept for my PCB. So my idea of learning is just to take every part and just experiment with it. So there are too many factors. That is what my expert advisor told me. So I've decided to completely stop because designing a motherboard has a lot of parts, such as these. It would have to have a GPU and a CPU. So it was just complex, and I would have to have a teammate to be able to since working on the hardware and the software side is pretty time consuming. So the PCB reflection. I should have designed the PCB that would just have made the screen turn on and some extra functions, or just use a pre-built PCB microcontroller like the Arduino or the Raspberry Pi. So the operating system. So when you want to build a sword, you want to make it out of silver, because no matter how much you sharpen the sword, it will still be better than a copper sword that is sharpened to the same amount. So the operating system limits your performance. So how I calculated these values are I ran a C++ program in Windows, and I calculated the milliseconds and then converted it to percentages. So we can see that Gentoo Linux performs 30% better, macOS 23%, and Windows 16%. So why? Why does Linux perform better than the alternatives? So it naturally does not have any unneeded programs. For example, Windows has Xbox Game Bar, has a lot of Outlook pre-built in, and it just contains a lot of stuff. So Linux removes all of that unnecessary stuff. So the processor control. To simplify it, registers are just temporary storage. I will write the firmware to the schematics that I am working on. So how I decided upon these 8 firmware is because these are the basic tools that are needed to power on a laptop and get it running to the operating system stage. So processor control is basically the decisions of the laptop. Memory management, it is a paging system. Input output, so connections. And so let's first move into bootstrapping. This is just where I set up the environment to run the stuff. Basically, when you go into the car, you have to seatbelt, you have to pre-check, look around. That is basically what I am doing. However, it was not good because I accidentally deleted part of my documents file, and because it runs on my system, so I have switched to a virtual machine. So everything I do in there is kept in there. So the processor control. Basically what I'm doing is I'm just initializing everything. The reason for the loop there is because, as you can see on the screen, there is GPIO 0 to 15. So it will just go down those iteratively, so like sequentially. So, for example, you can see I2C0 SCL. And I write to the I23 SCL to be able to initialize it. So how I did this is I basically just referenced the assembly sheet. So it's just documentation that contains every function that is in RISC-V. And I just related it to the PCB. So roadblock. The firmware roadblock is, so it is just like a lot of technical understanding of the topic, which I am not good at. I just get the general knowledge and I experiment with it. And for like hardware design, that is pretty good since you can actually see the real physical result of it. But like for like more like abstract topics like firmware is not too good. So the device drivers. Linux comes pre-configured with device drivers, and to configure it, you just have to run these commands in the terminal. So the firmware reflections. So overall, I am decently happy since I've at least gone through like a few firmware operations and like connected it back to the PCB, since it is a proof of concept. So revision period. So what have I not worked on? So now I look back at the laptop and like I forgot a crucial part of it. It's heat. So basically the thermodynamics of the laptop. Because if the laptop is hot, then it basically hinders all the operations, the performances, and it doesn't make it a laptop anymore. It makes it a hot top. So I basically plugged in this equation, and if you want to see the calculations, you can come to my stand. But I basically, what I'm doing is I'm plugging every value in and just getting the radiation constant. So let's take an example. So I think I graphed this wrong because I don't think the PCB should be at like 30,000 Fahrenheit. But but I just wanted to give a showcase of like how radiation just radiates out. So how I'm gonna use this graph, this is an example. I just put a bunch of thermal paste at the areas where it is most hot. Then the least amount where it is least hot. Boom. So this would be my end of revision. So this is a quote that I came across. I alone cannot change the world, but I can cast a stone across the water to create many ripples. So this would basically be an inspiration as to why to join STEM Capstone class. And thank you.
Any questions?
You said you use the virtual machine. Was that actually virtualizing a RISC-V architecture, or was it virtualizing it?
I was using the Gen 2 Linux RISC-V like Turbo.
Do you think it will be possible to use other electronics like a cell phone?
Or what?
Like something like a modular computer, but in a like small space, like cell phone? Do you think it will be possible?
Modularity in cell phones?
Yeah.
Well, personally, I think because of the compact size, cell phones have like no space for that modularity, but like in Samsung phones, they have a battery which you can just take out and replace it if it like gets low on that end of its shelf life. So like yes, it would be able to. The cell phones will be able to modularize. Any more questions?
All right.